I am Daphne Kounali, lead statistician at the Oxford Clinical Trials Research Unit. This is the final lunchtime seminar in the BRC Statistics Hub seminar series. It provides a broad overview of multilevel models in clinical trials. I will explain what multilevel models are and why we need them. I will guide you through an example using data commonly encountered in clinical trials, gradually increasing the complexity to illustrate the components of multilevel models. I will also talk about the software we use to fit these models and how to interpret the output. I will finish with exploring the broad modeling approaches for extracting information from structured clinical data, aiming to develop a clear understanding of the differences in inferential targets between marginal and conditional models. Longitudinal studies are common in modern trials and cohort studies. Contemporary clinical trials use increasingly sophisticated designs that require us to accommodate complex structures. Imagine we're interested in the pain experienced by patients undergoing certain type of surgery. Patients are followed up over time with interventions delivered at various hospitals or sites by different groups of healthcare professionals. For example, in surgical interventions, different surgeons may be involved. Additionally, participants can be assessed using various methods, collecting patient-reported outcomes from multiple sources. For example, in pediatric trials, patient-reported outcomes might be gathered from both the child and their parents. By taking multiple snapshots of a group over time across various settings and sources, we can obtain data that accurately reflects the world in its realistic complexity. This approach allows us to capture both between individual and within individual dynamics, enabling us to study more complicated hypotheses. For example, in a longitudinal design, we can examine the effects of the interventions not just at a specific time point, at one snapshot, but also look at the effects, whether the effects of the intervention are maintained over a period of time or change over time. Additionally, we can explore individual or other context-related factors that may influence the effectiveness of the interventions. Complex data structure can provide a more comprehensive understanding, but they also introduce greater complexity in our modeling. We can ask different questions. In clinical trials, we're typically interested in the marginal treatment effects. But what do we mean by that? What is the difference in the average pain, as we've seen in our previous example, of a randomly selected patient treated with a trial intervention and a randomly selected patient treated with standard of care? However, there is variability in patient outcomes or the way the treatment is delivered across different settings, across different hospitals. And for these reasons, we might be interested in a more nuanced question. This is what we call a conditional treatment effect. What is the difference in average pain of a randomly selected patient within a hospital treated with a trial intervention and a randomly selected patient from the same hospital treated with a standard of care? So in this case, we are taking into account the variation that we know is present across different settings, different hospitals. We may also be interested in the actual variation in treatment effects. How much variation is there between hospitals? And how much of this variation can be accounted for by different hospitals? Or how much of the variation is due to between individual variation? How much variation is there between individuals over time or in the way they change over time? Do the level or the rate of change vary across different groups? This could be the patients themselves, hospitals, or perhaps geographies. How does time-varying covariate predict an outcome? In the example that follows, I will focus on the most common dependence structure encountered in clinical trials. This is a longitudinal design where patients recruited across different hospitals and followed up over time. Let's begin with a straightforward standard linear regression model used with cross-sectional data. In this model, each individual contributes one observation, but not everybody is observed at the same time, and we're interested in how the outcome, y, changes over time. On the y-axis, we have the outcome indexed by individual participant j, while time is represented on the x-axis t. We can fit a linear regression model to this data. The coefficient beta 0 represents the average outcome at time 0, and beta 1 is our slope, which quantifies how the outcome changes as time progresses. The term EJ, residual, symbolizes the residual error, which measures the distance of each individual observation from the optimal fitted line. The statistical method is designed in such a way to provide us with the optimal solution that minimizes the residual error overall. Now, let's expand on the concept and make things a bit more concrete and a little bit more complicated. Imagine that our outcome variable y represents weight, and we're interested in modeling weight and understand how it changes over time. We know that individual weight changes differently for each individual, which is why we collect now multiple observations from each individual. Here we have 3 individuals represented by colors blue, green, and red, and each individual is observed multiple times at different time points. Let's assume for the moment that there is no growth, so our model only has an intercept, and this intercept represents the average weight across all observations. All these observations from the different individuals have an overall average, the population average weight. Each individual has its own average, and this is quantified by the individual level intercept, individual level residual U0. You can see how this quantifies how far away each of these 3 individual averages differ from the overall population average weight. Additionally, the observations from each individual will vary around their own individual means. These deviations, EIJ, indexed by occasion I for individual j, are deviations of each of the observations for the blue individual from the individual mean weight of the blue individual. Similarly, we have residuals for the green and the red. These are called the observation level residuals, EIJ. Let's put everything together now in one model and see the equations. So we have an individual weight y, for occasion I and individual j. We assume no growth for the moment, so time is the same for all. So each individual has its own mean, beta naught j, plus some residual error, EIJ. Each mean is centered around the population mean, weight b naught, plus some individual level residual, U naught j. The way we estimate this residual, individual level residual, in a statistically efficient way is by estimating the variance, sigma U naught. What we're saying here is that those individual means vary around the population mean, and this variability is summarized by the between individual variability sigma square U naught. Additionally, we also have the residual error or observational variability, or now within individual variability. Let's see how we interpret these parameters of the model. So beta naught, we said, is the overall population average, the intercept of the model. U naught j is the individual departure from the population average, sigma square u naught is the variability of all these individual departures from all these individuals u naught j, how all these u naught j vary, is summarized by the sigma u naught, the individual between individual variance, and EIJ is the observation, and in our case, because we have time, the occasional level residual, and it represents the difference between observed and what would be predicted for the particular individual. Let's introduce some terminology as well. So in multi-level, here in this model, we have two levels. The level 1, we refer to the lowest level, or the individual measurements, in this instance, the individual observations, and the level 1 residuals, occasion level, or observational level residuals, EIJ. At level 2, the next level up is represent the study participants, and the level 2 residuals describe departures of individuals from the population average. Let's make things a little bit more concrete and give some names to our blue, red, and yellow dots. And let's say that we have Tim, Bob, and Vic that visit a clinic at different ages, and their weight is measured. This first simple multi-level model is a prediction model. Is a prediction model for each individual's observations. Each observation for Tim, Bob, and Vic can be predicted through an equation that has three parts. The overall mean for Tim consists of beta naught, the population average, and another term that quantifies how much Tim's mean deviates from the population mean, and a third part that tells us how much each of Tim's observations deviates from Tim's individual mean. And using the terminology we just introduced, the three parts that make up the prediction for Tim's, Bob, and Vic's prediction at each time point will consist of three parts: the population mean, Tim's, Bob, or Vic's level 2 residual, and Tim's, Bob, or Vic's level 1 residual. And the way we specify this in the Stata software is by using the xtmix command, which has two parts separated by a double pipe. In one part, we have to specify the fixed part of the model, and in our case, the fixed part of the model is the population average, or the intercept, and the random part of the model that specifies the variance components, the level 1 and the level 2 variances. Let's see how the Stata output looks. Here is the Stata command for fitting a random intercept model using xtmix with the data we described. For the fixed part of the model, specified on the left-hand side of the double pipe, we have the outcome variable WT representing the weight of these boys and no other predictors. In Stata, the intercept is implied, though this may not be true in other statistical packages. On the right-hand side, we specify the random parameters, which in this case is the grouping variable used to identify different individuals labeled as ID. The comma in Stata introduces options for each part of the model. Here we use the option bar for the random part to indicate that we want the random effects expressed on the variance scale instead of the default standard deviation scale. Stata returns output that includes summary statistics, indicating that we used 1,835 observations from 367 individual boys. The overall average weight was 43 kilograms. In the random effects section, we obtain estimates for the variance components. At level 2, we see the variance between individual boys and the variance and the residual level variance, which quantify the remaining observational level variance, encompassing both random variability and measurement error. If we had multiple observations within each measurement occasion for each buoy, we could separate out measurement error by including an additional level for these repetitions. Let's add some complexity to make the model more realistic, as we know that the weight of growing buoys changes from childhood to adolescence. Therefore, we need to include time into our model. How about using a fixed intercept and fixed slope model? Could that work? Returning to our scatter plot that displays weight against time for 3 different individuals, each represented by a different color, we can now also observe the overall slope based on all observations. We can also see each cluster of observations from each individual. The variability within each cluster is much less than the variability between clusters. Observations within a cluster are more similar to one another compared to observations across clusters. Therefore, if we disregard this clustering, the observations alone will deviate significantly from the overall slope. We need a proper growth model. So let's describe a random intercept and fixed slope model. A random intercept model is a model where each individual is allowed to have its own intercept. We have now introduced time in the fixed part of our model. A fixed part has an intercept and a slope. The intercept describes the average at time 0, and the slope represents change in the outcome for each unit change of time. In a random intercept model with a fixed slope, each individual has its own intercept, but the slope is fixed and follows the population slope. So the individual trajectories over time are different from the population slope, but are parallel to it. The deviations of each observation in a cluster from its own trajectory is now much less. The residual observation variability has now decreased a lot. A simple but proper growth model now with a random intercept and a fixed slope in equations. Outcome y, in our occasion weight, indexed by occasion I for individual j, and t, time, indexed by occasion I. Here we assume individuals are observed at the same time, but it doesn't have to be like this. The outcome y has an intercept, beta naught, indexed by j, so it is not fixed, it varies across individuals, that's why it's indexed by j, and a slope beta 1, the slope is fixed. Beta naught j is centered around the population slope beta naught, the population intercept beta naught, and each individual deviates from that by an amount u naught j, the individual level 2 residual. The variability of all these deviations for all individuals from the population intercept is captured and summarized by sigma square u naught, the between individual variability or level 2 variability. The residual observational level variability completes the specification along with the assumption of independence between these variance components. These equations are prediction equations for each of Tim, Bob, and Vic. The prediction for Tim's weight at age 7 is made of the overall population intercept plus how far away Tim's own intercept is from the population intercept plus the population slope multiplied by age 7, and which runs parallel to the population slope because this is a fixed slope model, plus how far away Tim's individual observations are from its own line. The model is specified in data in the same way as before. The only difference is the introduction of time as a predictor in the fixed part of the model, the left-hand side of the double pipe. Clinic is the variable capturing time in this data set. The starter output after fitting this model with a random intercept and a fixed slope gives us the same parameters as before for the random part, differing only in the fixed part. The fixed part now gives us an estimate for the average weight for the earliest clinic visit, constant, and an estimate of how this changes at every visit. The random part gives us an estimate of the between individual variability for the intercept, constant, and the residual variability, just as we did before. Now, with the more realistic estimates for the fixed part of the model, we do see significant reduction in the residual error variance. Having estimated these models in data, we can produce prediction for each individual boy. And here we plot the first 50 from the 367 boys we have in our sample. These predictions are consistent with the model that allow each boy to differ at the first visit, but their trajectories are parallel to the population average trajectory. The boy's weight can change over time in different ways. We can implement this idea and test it by introducing more complexity in our model and fit a random intercept and slope model. The blue cluster represents a boy who not only starts at a higher than average weight, but the weight increases faster than the average, whilst the weight of the green cluster starts closer to the average but changes with time in a way that's very different for the population average. So in this model, individuals are allowed to vary around the starting point, with the blue cluster starting higher, the green closer to the average, and the red cluster lower than the average. So it allows for individual level intercept residuals, but also allows how these blue, red, and green clusters change over time. It allows for individual level slope residuals. Back to our model equations again. With this new model, we have some additional parameters to specify. In addition to the individual boy departure from the population intercept, now we also have departures from the population slope, with beta 1 no longer fixed but indexed by individual j. This individual B1j is centered around the population slope B1 plus some residual, the individual slope residual, representing each boy's departure from population slope. The variation in slopes across individuals is summarized by the variance term sigma square U1, and the intercept and slope random components can be allowed to be correlated and estimate their correlation. This is the most general form of the model. The remaining elements of the model specification are the same as before. And our predictions now for team's growth at age 7 is more refined and not only has individual departures from the population intercept, but also from the population slope. And his residual error now will be even smaller. Instead, we can introduce the random slope in our model by adding the time parameter clinic 7 in the random part of the equation. And in the options, we can specify the correlation structure for the random parameters. We specify unstructured as this is the most general, although a number of different other specifications are available. If a correlation structure specification is not included, the default assumption would be independence. Let's look at the output after fitting this random intercept and slope model. You must have noticed that the time variable is now slightly different. This is because we recoded the time variable clinic, and it's called now clinic 7, and we recoded it in such a way that age 7 is now time 0. This way, the intercept represents the mean at age 7. This allows us to interpret the coefficients more easily. It's also a good idea to always center our data appropriately and standardize our predictions so that they represent the average covariate profile. Multilevel models are complex models and can be sensitive to different parameterizations, and predictor centering helps estimation stability as well as interpretation. Random intercepts and random slopes can be seen here. They're correlated positively, and the residual variance is now further decreased. In this graph, we have a spaghetti plot with the prediction trajectories for the first 50 boys resulting from this new model. These weight trajectories are no longer parallel. We can see that these are fanning out, and this is consistent with the estimated positive correlation between intercept and slope. This means that boys who start smaller gain weight slower, whilst bigger boys gain weight faster. In infancy, patterns of individual variation in growth is different. There we usually see a negative correlation pattern with trajectories fanning in, and this implies that smaller babies grow faster than larger ones. These varying slopes can be thought of as interactions between group-level indicators and individual-level predictors. What if we center time at a different point, say age 15? This model hasn't changed, but we can see that the intercept estimate has changed and the random part of the model has changed. This is because this parameter now, the intercept, represents a different quantity, and this is the average weight at 15, which is much larger. As a result, the random components have changed as well. As previously mentioned, we should always be careful on how we parameterize the model to help us with the inferences we want to focus on. It may not be a good idea to center our data at time points where not many individuals contribute observations, since usually there is loss to follow up. Introducing a random slope in our model introduces complexity to the patterns of between individual variability. Between boy variability in weight now also depends on age. We can calculate how this variability changes over time using the random effects variance we have estimated in our model. This is a quadratic function of time strictly increasing with age, as implied by our fanning out pattern we've seen before. And this is the plot of the calculated between boy variability in weight as they grow, along with 95% confidence intervals. Bear with me with a little more jargon. BLOOPs and shrinkage. BLOOPs stand for the best unbiased linear predictions. Estimates that we saw in our spaghetti plots for estimating the weight for individual boys. These are shrunk towards the population mean trajectory. They are weighted average between the individual and population average intercept and slope, and because they are shrunk, they give us a more robust and less extreme group level estimate than the raw data. The amount of weighting depends on the correlation structure, the degree of similarity between individuals or within individual variance, cluster size, and between individual variability, and overall sample size. Shrinkage gives us a sense of how much pooling is being performed for each group of parameters. In our case here, intercept and slope. The amount of pooling depends on the heterogeneity between groups and the information available within group. It does require a further post-estimation work to understand how the model works. In a simple scenario where we only have an intercept, random intercept, we will have no shrinkage if between individual variability is much larger than the average residual variability. This can happen when we have a highly heterogeneous sample of individuals, or we have little measurement error, or large cluster sizes. We get more shrinkage when individuals are similar, and there is little reason to believe that any individual deviates from the overall means, or in cases that we have noisy data and moderate small sample sizes. Random fluctuations can make up the majority of the raw data estimate, and with shrinkage in multi-level models, these are naturally de-emphasized. Mixed effects models are not the only modeling class that can accommodate correlated data. Generalized estimating equations also accommodate repeated measures and provide valid standard errors without explicitly modeling the correlation within a cluster. However, they are restricted in the complexity they can accommodate. They can accommodate only single-level clustering. They are not designed for inferences about the correlation structure, whereas in our mixed effects models, we can provide confidence intervals for our error components. They cannot provide predicted values for each cluster, and they can perform poorly with unbalanced and missing data. There are fundamental differences between conditional random effects models and marginal models. They estimate different quantities. Marginal models target population average effects, where random effects models target effects specific to clusters. Although there's no substantive difference for continuous response in linear models, but they can be very different in nonlinear models. Mixed effects models are flexible and versatile tools allowing us to explore data with complex dependent structure, particularly when we're interested to understand more about the individual clusters and identify those with the highest level, say here of an outcome such as BMI. A longitudinal model can be further extended to include an additional level of nesting within countries, and we can use the country-level random effect to rank country. One needs to be aware of the interpretation of these confidence intervals here, which reference the overall average, and it is tempting to use them to compare countries, but that would be wrong. In summary, multi-level models or mixed effects models is a statistical tool for analyzing data with complex dependent structure. This means structures where observations are nested within individuals over time, across hospitals, surgeons, or geographies. They are a member of a larger family of hierarchical models, and these can include non-nested structures. For example, we can have patients treated in hospitals but transferred in other hospitals, transplant recipients receiving organs from different donors in different hospitals. They have wide applicability. They combine information across levels efficiently in a single model and allow real-life complexity when making inferences. They have versatile application, repeat measures, measurement error, informative dropout, geospatial structures, multiple outcomes, meta-analysis, and evidence synthesis. They help us elucidate contextual effects and understand the heterogeneity in outcomes, but most importantly, they provide us with more precise estimates of treatment effects and individual predictions. The complexity, however, can be costly and usually require simulation-based inference through Markov chain Monte Carlo algorithms. Thank you.